speak about the divergence theorem because I think that it's one of the most important theorems of contemporary analysis. It is a theorem on pathing from integration from the inside of the domain onto the boundary. I mean that the meaning of the theorem is divergence theorem operates with vector fields. It's the unique theorem among the other Stokes-Tie theorem operating by vector field. And this is what causes that it has a large spectrum of different applications. Some of them very striking applications will be shown later. To formulate the theorem precisely, we need to introduce some notions, namely the notion of outer vector field normal to the boundary. Assume then that D is a bounded domain in Rn with a piecewise smooth boundary. Could be a weaker assumption about smoothness of boundary, but still. At every point of smoothness of the boundary, there is exactly one outer unit vector hooked at P. It is unit vector orthogonal to the boundary and pointing outside. All such vectors constitute a vector field defined almost everywhere on the boundary, and this unique vector field will be denoted by N. We will call it the outer field normal to the boundary. So this is our first notion. The other notion is that we have to construct two volume forms, one inside of the domain and another at the boundary. Assume that we are in Rn and we have a domain D. The standard volume form of such a domain, in fact, which it is defined in the whole Rn, is given by the determinant. So omega D is the volume form of D, acting on a sequence of vectors, x1, xn, is simply the determinant of vectors. So vectors are just rows or columns of the matrix. Omega D, this volume form in Rn defines the unique form on the boundary in that way that we use just constructed before normal vector. Namely, if we substitute to our form of Rn normal vector, we get the form which is degree less by 1. So right to be a form of the boundary. So this form is defined that way. So with respect to vectors, we have the following definition. So we have film which is normal to the boundary and two forms, one of the domain and another on the boundary. The theorem says that if D is a bounded domain in Rn with a piecewise smooth boundary, and if we have a vector, any vector, arbitrary vector, smooth vector field on D plus the boundary, then the integral of divergence of such a field over the boundary is equal to the integral over the boundary from the scalar product of vector field and N. Look that since that the vector field N is unit vector field, it means that this is just a measure of projection of X onto the vector N. Here, omega D is the standard volume, omega delta D is the volume of the boundary just constructed. Divergence is the divergence of the field. We know the formula for the divergence here, N. This is the standard scalar product, and xn time n, this is simply such a sum of products. Of course, an analogous theorem holds in much more general situation, namely on a Riemannian manifold with an empty boundary. This situation differs by this Euclidean situation that the metric, that the scalar product depends on the point. In Rn, we have universal scalar product given by this formula. On a Riemannian manifold, we have that this product, which has the same properties of all the scalar product of the world, but it depends on the point. But if you formulate the theorem, the formulation will be the same. You have to change only domain D onto manifold M, which means that it's also something like a domain having a boundary, and everything is very analogous. We have now a new scalar product on M. Then we can construct the unique volume form if the manifold is oriented, that is unique scalar form. And again, in the same way as before, we construct the form of the boundary, because also here a field of normal vector fields is well defined. Divergence is the divergence of x. X is a function, this time defined as by this formula, a little bit different. But in this particular situation of Rn, it is simply usual divergence considered before. Lx is the derivative in direction x. I would like to present two surprising applications of the theorem. First of all, if you remember the Archimedean principle about buoyant force acting on an object in a fluid, so I will prove here that this very important physical principle that is a long time because it was discovered over more than 2,000 years ago, and saying the buoyant force acting on object immersed in fluid is equal to the weight of fluid displaced by the object. To simplify situation, to do it more mathematical, first of all, assume that our fluid is just water. It would be easier because water has unit specific gravity, 1 gram over a cube of centimeter. Take a coordinate system in R3, coordinates are x1, x2, and 3, and assume that the half space R3 minus is filled up with the water, Then the upper surface of the water will be simply x1, x2 plane. The vector field representing downward pressure, being the effect on Earth gravitation, is proportional to the depth. So in our case, this field will be, this just 1, this our, because it's water. If not, it would be just another number. Our field is of this form. The opposite field that represents the buoyance force being up, because this is going down, this is going down, represent the buoyance force. I presented on the picture. So it is our coordinate system. Everything which is under the plane x1, x2 is under the water. In particular, we have an object being under the water. And here we have two vector fields, x, which is red, and y, which is green, the same formula as before. Look that the divergence of y is -1, because this is the formula, so it is divergence. Now, the buoyance, we have a sketch of the boundary. It's our boundary, and we have a point and the vector normal to the boundary. Of course, the buoyant force acts on each point of the boundary. This is our force y, hooked at the point of the boundary. We have to project it onto this and integrate over the boundary to get the global buoyance force acting on the body. Let's do that. What is the volume? Volume is 1 times this one, but this is no, enough. I will have it here. Assume that the physical solid body is immersed in the water represented by domain D, with the boundary partial D being a two-dimensional closed surface. The total value of the weight of the water expressed by D with the specific gravity will be, this will be the weight of water displayed, volume time this our one. But this is integral over the boundary. But this is divergence 1 times this one. On the other hand, the total value of buoyancy force is equal to the integral over D from inner normal component of y acting on the boundary. So the buoyance force is represented by the integral over boundary just y and negative n, and this is negative y n over this one. Now, Archimedes, almost 200, more than 200 years ago, said these two integrals are equal. So the Archimedean principle is saying that two obtained integrals are equal. But look, this is exactly the divergent theorem for our field. Why? The next example, also from ancient times, the proof of Pythagorean theorem. We all know the Pythagorean theorem for triangle, but it can be generalized, for example, to most complicated figures, simplexes. I will formulate it. Simplex, what is simplex? Take n+1 points and define the set which is a convex hull of this, the smallest convex set containing these points. Then the sides of the simplex are of 1 dimension less. So to get the side of the simplex, remove one of the points from the sequence and again do the same, take a convex hull on these points. Then you get a simplex. Examples, 2 different points determine 1-dimensional simplex, namely a segment. 3 different points not lying on a straight line determine 2-dimensional simplex, a triangle. 4 different points not lying on a 2-dimensional plane define a 3-dimensional simplex, a pyramid, and so on and so on. Here we have 2-dimensional. Here we have 2-dimensional simplex, 3 points, rectangular this time. But look, every rectangular triangle can be placed in the coordinate system that way that this vertex at the right angle will be the origin, and there are 2 points on the axis. So if we have orthogonal coordinate system, we will take this exceptional vertex, and other vertex are simply each on each axis of the coordinate. We have in this instance that Pythagorean theorem saying that the measure of hypotenuse is the sum of squares of lengths of these two sides. But the situation repeats when you take three-dimensional space, a vertex here, 3 points A, B, C on the axis, and you have the following pyramid. And then you can check this because it is a school calculation that the area of this covering, is sum of squares of measure of these triangles. This one front, that one bottom, and this one lying behind. And of course, it can be proved that it is the same in any dimension. So take a simplex. Assume that the simplex is straight, rectangular, orthogonal. It means that all the faces of this point, with remove this point, are just orthogonal each to the other. So each faces, instead of this cover, are orthogonal each to the other. Consider n-1 dimensional measure of a side. Then the Pythagoreans says that this one, defined by the point 0, lying opposite of the coordinate system, and the measure squared is the sum of square of all the others. The proof of the Pythagorean theorem via the divergent theorem. I found this proof in this beautiful, very short paper from 2001. It's so nice that I decided to present the proof. Denote by alpha j the measure of the side Sj. Take any constant vector field on Rn, then of course divergence of such a field is 0. If this is 0, it means that the 0 is integral over D, where D is the simplex, of the divergence. But this is the integral over the boundary by the divergent theorem of scalar products x at n, when n is the vector, outer normal vector, unit vector to the boundary. But the boundary in our case, in the case of sequence, is a sum of sides. So this integral will be just a sum of integrals, each over a single side, and the same as here. But this is a constant field on this side, and this is a constant field, could be put in front of the integral, so we get this one. But we get here the integral over the side with the volume 4 of this. It means that it is an n-1 measure of the side as yod. It was denoted here as alpha yod. So we have this one. This is constant, this is constant, this is constant, so we can put this alpha yod, alpha j here. So we get finally that 0 is this sum of scalar products, but this was completely arbitrary vector field. and scalar product is positively defined, this means that this have to be equal 0, this sum. So we get that this sum have to be equal to 0. Remove one term from this side. This were index 0 on the left side. So we get this one. And if we multiply this equality by itself, then by orthogonality we get this one, which is exactly the theorem of this shape. Now, studying these things connected with the Pythagorean theorem and generalization, Archimedean theorem and generalizations, I discovered that the divergent theorem can be formulated in much more general situations. First of all, in the case of arbitrary manifold, and not only for vector fields, but on any vector valued form of any degree. So our aim is generalize the divergent theorem to vector valued form, differential forms of any degree. Such a form as sections of such a bundle. Vector, it means that it has to be tangent bundle. Of course, for k equals 0, this is cancelled, so you get simply a tangent bundle as sections of such bundles are simply vector fields. Then I use the definition by Rumler from the paper Differential Form, Weissenberg formula, and so on, published in 1989, when he introduced two operators of gradient and divergence, just operator we need for formulate the divergent theorem. So the gradient is operator from usual scalar form to vector forms, defined by the formula where J, K is zero order operator of this form. And gradient of a form behaves similarly to the gradient of a function. Function is simply form of degree 0 and has very nice properties. He also defined the notion of divergence, going in opposite direction from vector fields, from forms with vector valued forms to scalar forms, and defined by the formula that is trace d plus d trace, where trace is defined in the usual way. The trace of phi of vectors x1, xk is simply a trace of this automorphism of the tangent bundle. So we have two notions, gradient and the divergence. And now let me formulate the divergent theorem for such objects. Theorem, the Riemannian case. So we are on Riemannian manifold n. Let M be a compact oriented Riemannian manifold of dimension n with smooth boundary. Then for any vector form and for any test form, phi, psi, of the same degree as this one, we have the integral over this vector form over the boundary. So again, a projection, a kind of projection of the normal direction is the divergence forms scalar product with our test form. Unfortunately, in this general case, we have one more term with the gradient. But we can always look at the test form such that the gradient is to be 0. Then the situation simplifies. Now, if we consider take the theorem and consider the particular case k equals 0. So our vector form phi will be simply a vector field. Take the test form psi equal identically 1 and then we will have from this formula that this form being under the integral here is x, and the other is divergence x. So in our case, the formula 7, our formula 7 reduces to the usual divergence theorem in its classic version. In the Euclidean case, so for Rn, the situation simplifies essentially. Namely, we can use as a test form, we can take a coordinates system, and we will take as a test form, this K form, from the basis of forms in R. If we substitute, if we calculate all the things here and substitute to the integral, we get that theorem in the Euclidean case. So let D be a bounded domain in Rn with smooth boundary. And again, vector form. And our test forms, just to get the test form, choose a sequence of indices. Then the theorem will take a form that phi with indices I1, Ik, scalar product with n, is the divergence of this one over here. So very similar to its classical origin. Okay, some conclusions. The divergent theorem has a wide spectrum of surprising applications. The uniqueness of theorem follows from the fact that it is of vector character. Vector fields play, namely, an essential role in mathematical, physical, and engineering applications. The examples are dynamical systems, vector fields, mechanics, vector fields, analytic dynamic, vector fields, static and dynamics of gases, liquids, and solid bodies, vector fields. If a manifold represents a mathematical or physical object, a vector field represents forces acting on the object. In physics and engineering practice, the values of the force displacement can be often measured only on the boundary. We don't see what is inside. Well, you can measure the things on the boundary. The divergent theorem gives then some information of what is happening inside. A possible inhomogeneity of the material of the body, or its composition from different layers, can also be accepted within the Riemannian structure. The inhomogeneity is then carried out throughout correction of the Riemannian metric. Layers can be represented by foliation. Note also that the vector character of the divergence theorem allows setting up systems of non-trivial boundary conditions when solving boundary value problems for differential operators on M. For example, in the theory of elastic body, 4 differential, non-trivial, but natural conditions are considered: Dirichlet, absolute, relative, Neumann, and all of them can be investigated. The condition when were investigated in the paper in detail in our paper, in my paper with Kozłowski, natural boundary conditions for weighted Laplacian, published in Pisa. Look, the conditions are very interesting because Dirichlet is usual, that there is for form, scalar form. tangent and normal part are zero, which means that it's usual Dirichlet. The form is zero on the boundary. Neumann is also similar to the Neumann because there are two operators, co-derivative and derivative, and tangent and normal part of them are equal to zero, which means that the normal derivations of the form are zero. But there are two other conditions that are absolute and related, and they have also a physical meaning, physical applications. The result will appear in the paper, the divergence for a vector valued forms is to appear. Thank you very much for your attention.
Thank you very much. Any question or comments? Well, it's very impressive story, obviously.
I'm very wrong.
Nice.